So today, I'm taking a leaf out of everyone's favorite math lecturer. I'm going to start with the question, what is cryptography? And this is not a trivial question. So for a while, humans sort of knew how to do ciphers. There's, of course, the famous Caesar cipher and some variants of this, the Vigenère cipher. But humans didn't really understand what cryptography was supposed to be for quite a significant amount of history. And it wasn't until really the mid 20th century that cryptography started to properly take shape. So my claim is that the goal, oh, that's too thick. The goal of cryptography is to construct systems. I'm being deliberately vague about what exactly that means. Systems of some kind to achieve some goal and prove their security. So both of these are kind of nebulous. It's quite difficult to really define what they're supposed to mean. I'm going to start by attacking the systems thing. So if you know a little bit about how cryptography is used, you might be thinking, okay, there's symmetric cryptosystems, or also known as ciphers. There's asymmetric cryptosystems. We can do key sharing. We can do digital signatures. So I'm going to start by saying that a system, in some sense, is a set of algorithms, and not just any algorithms, but algorithms that we can compute. So a set of efficiently computable algorithms and they have to satisfy some correctness condition. So for example, for a crypto system, if you encrypt something and decrypt it, hopefully you get the same message. Okay, so what's an algorithm? What does efficiently computable mean? We're going to procrastinate that until well into the future. So I'm going to start by, you'll notice when theoretical cryptographers talk, we kind of try to avoid symmetric cryptosystems or ciphers because they are quite theoretically ugly. So I'm going to talk about asymmetric cryptosystems. This is that public-private key thing that you've probably heard about. The idea is you can use a public key to encrypt a message, but only I, with the private key, can actually decrypt that message. So an asymmetric cryptosystem okay, so it's a tuple of algorithms, some way to generate keys, some way to encrypt stuff, and some way to decrypt stuff. And gen, I'm going to pretend it's a function, even though it's not really, takes a natural number, a positive natural number, gives us a public key and a secret key. So it maps a security parameter of some kind. Again, I'm being really vague about what exactly that is. To key pairs. Well, and I'm going to call them PK, SK of length lambda. So I have some key of a known length, and my encryption map is going to take a public key and a message. We don't have to be, if you like, you can think of the message space as lambda bit binary strings, but we don't have to be too specific about it, to a ciphertext space. So it encrypts, right? So enc pkm equals c to encrypt. And I should stress that all of these probabilistic, right? It wouldn't be a very good crypto system if we always generated the same key. And a good deal of the theory that we'll do later in the semester is really trying to understand what this probabilisticness means. At the end, we'll arrive at some standard idea of a Turing machine with a random tape, but we're not worrying about that just for now. And of course, we have the decryption map that's going to take a secret key and a ciphertext and give us a message. And the correctness. Oh. So the correctness says for all lambda. If we get a key pair out of the generation algorithm, this arrow is going to mean something along the lines of sampling. Then for all our messages, if I decrypt a ciphertext that I get from encrypting, I get the same message. So this is our idea of a system, and it's a concrete example where it's a bunch of probabilistic efficient algorithms. It wouldn't be much use if the decryption was inefficient, because then we could never compute it, such that it has this correctness condition. And the correctness condition is what we might expect, right? That we can decrypt messages. Okay, so that's the first question answered. Easy.
Till the
I'll just wait for people to...
Sorry.
Yeah.
Sorry, I should have provided some instructions. Yes.
Yes. I'm not familiar with how these orbs work.
Yeah, so the camera's following this for the recording, and if people choose, they can listen through this orb. So
I see.
It's actually set to follow me because I didn't want to burden you with these instructions right away.
Yes. No, makes sense.
It means that when you move to a new board, I have to follow you, and then the orb will follow, and then we can start on the board. So you can go ahead.
Okay, so we've answered the question, what is a system? Sort of. We haven't answered it very mathematically, but we've answered it conceptually. Now, what would it mean to say this is secure? This is quite a complicated question. And the way that we're going to approach it today is through a game. Hope you like games. Games can be either computational. So if I have a group generated by some generator given y equals g to the x, find x. This is the discrete logarithm problem, and it's a computational problem because you have to actually give me an answer, right? You have to find a value somehow. There can also be distinction or distinguishing games. So an example might be if I give you g to the a, g to the b, g to the c, decide whether g to the c equals g to the ab. So you output a bit in this case. And the idea, this is the decisional Diffie-Hellman game. The idea is you're somehow telling apart a group element that's constructed in a specific way from a group element that's just chosen uniformly at random. That's why we call it a distinguishing problem. The idea of a computational game is a little bit more complicated. The way that we usually think about security in this classical sense is distinguishing. And we're going to see that actually you can sort of lift this distinguishing idea to pretty much everything. And that's going to turn out to be the key idea to universal composability. All right, so we have interactive algorithms.
Question about
yes.
I'm not familiar with the second of these. So In the former case, generally it's important that finding an answer is difficult, but verifying it is easy. But it doesn't seem to me that there's anything similar to be said in the distinguishing case, is there? I mean,
So the idea is I know, I am the challenger. I know whether I've given you a uniformly random element or not. You have to decide whether or not I did. So if you say yes and I didn't, and I actually gave you, if you say that I gave you a uniformly random element and I actually did construct it this way, you lose. I guess the objection, right, is maybe I just happen to uniformly choose G to the AB, right? And this kind of ties back to this sort of information theoretic idea that you might encounter in cryptography. A lot of the times, there's a very small chance, 1 over the size of the group, that just by pure luck you guess the right thing, and we sort of discount that. We say it's such a small probability that it basically doesn't happen. Especially because the order of the group is usually something like 2 to the power of 2048, right? It's not going to happen. Does that answer your question?
yeah, I guess. Yeah, it's very interesting. I think I'll
Yeah,
wait for you to tell me more about this second thing, but I
yeah.
haven't heard of this. I've looked at this before.
Yeah, digging into this theory gets quite thorny quite fast. That is a completely true statement. Okay, so the setup here is we have interactive algorithms, interactive probabilistic polynomial time. Probabilistic. This is quite a mouthful, so I'll abbreviate in a second. I'll just call this PPT. Now, if you're coming at this from like a models of computation perspective, your mind goes, okay, so it's a probabilistic Turing machine that evaluates or gives an answer in polynomial time always. What's this interactive thing? Yeah, that's quite complicated. So for now, I'm hand waving, and we will eventually decide what this actually means. But somehow the idea is supposed to be clear, right? We have 2 computers that are talking to each other somehow. They're allowed to sample things randomly according to distributions, and they have to be efficient. They can't use an exp time oracle or anything like that. Algorithms, and we're going to call them A for adversary, and C for, oops, I meant to write that in blue, C for challenger. So the idea, yes, yeah, so you have some mechanism where they can write to each other's tape. In the case of 2 parties, this is very straightforward. In the case of lots of parties, getting it to actually work turns out to be quite technical. But in this case, it's, yeah, as you say, it's straightforward. You invent some mechanism where they can write to one of those tape and they can read off the tape and communicate that way. So the idea is the adversary knows the challenger knows, say, the secret key, and the adversary is trying to win some distinction game that involves this secret key. And we look at the transcript of their interactions. So what did C say to A? What did A say to C? And then based on this transcript, we decide whether or not the adversary won. Okay, if they win the game, we say the game outputs 1. So you can imagine the game as like some algorithm, right, that runs the Turing machines and at the end decides whether or not the adversary wins. So our first real definition, and recall we've got this asymmetric cryptosystem, we're trying to decide whether it's secure. And this is sort of the basic notion of security. So the indistinguishability, I write this in blue, the indistinguishability under chosen plaintext attack game. That's a lot of words that we don't have to worry too much about. I'll write it as this. That's a function of the adversary algorithm, where S is some cryptosystem, right? So it's some tuple of these algorithms that satisfies the correctness condition. And I'm going to specify it using some kind of instructions. I'm not going to mathematically define what it is, what object it is. I'm just going to say what happens. So first, the challenger is going to get a key pair out of the generation algorithm. Notice the game is parameterized by lambda. And it's going to send the public key to A. One important consequence is now the adversary can encrypt however many messages they want. They have the public key. They can encrypt lots and lots of stuff as long as they do it in polynomial time. So they can't encrypt literally every message. That would be exponential in the security parameter. Although even if they could, that still would not break the system, as we'll see. Okay, so adversary has the public key. The adversary is going to choose 2 messages. And it can choose them however it likes. Maybe probably uniformly, maybe it cleverly chooses something that will cause a corner case. It doesn't matter. And is going to give those messages to the challenger. Now the challenger samples a bit uniformly at random. In other words, it tosses a coin, right? And it's going to use that bit to choose which message it's going to encrypt. So given the public key, it encrypts NB, where B is the bit that it flipped, to the adversary. And now the adversary outputs a bit. And A wins.
Sorry, I just want to check I'm reading this correctly. So that's enc PK.
So this is the classic distinguishing problem. The adversary is choosing 2 messages and gets an encryption of one, and it has to decide which message was encrypted. And the idea is somehow this should be secure if you can never tell apart any 2 messages. If I see a ciphertext, I have no idea which message it is because I can't tell the difference. Even if I choose the messages myself, I can't tell the difference between 2 encryptions. Does that sound like something that you could reasonably hope for? That's an open question.
I think I'm still processing what the game is. So
the idea to summarize. The idea is the adversary is going to choose 2 messages, and the challenger picks one of them, encrypts it. Then the adversary has to tell which one got encrypted. So an immediate consequence of this, the encryption algorithm has to be randomized somehow. If the encryption algorithm is deterministic, then of course the adversary can just encrypt the messages itself and see right away which one was encrypted. So an interesting consequence, if you've ever seen this, so-called textbook RSA, where you take the message, raise it to the power of E mod the modulus, is not secure at all. Because this is deterministic, right? The adversary could always just raise M0, M1 to the power of E, check if that's the message it got. Check if that's the ciphertext it got. So we define security in terms of these games, and the idea is the adversary should have no better chance than tossing a coin. It has to guess, right? It could always just happen to guess the correct message. And I've run out of space on this board, unfortunately, so I'll write down the punchline on the next. Oh, still figuring out. Yes, we'll move to the next board. So, a cryptosystem, oops. So a cryptosystem is said to be in CPA secure if for all polynomial time adversary or probabilistic polynomial time adversaries, the probability that the adversary wins minus a half is in a class of negligible functions in lambda. And a negligible function it's this sort of not very enlightening analysis definition. So a function of the natural numbers is it's negligible if for all constants, all positive real numbers, the limit as lambda goes to infinity, f of lambda times, I did the thing. So c equals 0. Okay, so a function is negligible. This is a lot of math, but a function is negligible if it vanishes faster than any polynomial, right? So if I take any positive power, then it's going to still vanish faster than this. So for example, inverse exponentials are negligible, but so are a whole host of other things. And we ask that asymptotically, the probability that an adversary can win is negligible in the length of the key. And the hope is if you make the key long enough, this probability becomes so small that it will never happen. Now, the minus a half is in there because, as I say, an adversary can always win this game with probability a half just by tossing a coin, right? So there's a 50-50 chance that they happen to get the same result as the challenger. And we ask that they can do not much better than a coin toss. All right, so this is the basic working definition of security when you're not talking about these foundational theories. You define some kind of game and say, this is supposed to capture the properties you want our system to have. Of course, you can ask, is this really the correct property to have? And this is one thing we'll address. And this is simply what you take as granted. Now, so this works in some sense, right? This clearly provides some level of security because we're saying that the adversary can't tell the difference between two ciphertexts. Okay, that means that somehow it's supposed to be secure. But there are two key limitations. So the first is composability. What do I mean by this? Well, if I take an in-CPA system and use it to encrypt a key for another in-CPA system, is the overall system secure? How do these properties combine with each other? And with this definition, there's not really any way to tell. So if I share a key using an in-CPA system, system and use that key for another, is the overall system still secure? And you could try to reason about this in terms of somehow composing Turing machines, but it's really not clear what this might even mean. And in fact, we'll see in just a second a counterexample that shows these game-based definitions really do break down in practical scenarios. The other limitation is the strength. Like, I defined this sort of artificial game, right? How do we know that this really does capture the security that we actually want to do? So the guarantee depends on the game. If I define a different game, maybe this is more secure, right? Maybe I have some other game that some in CPA systems satisfy and some don't. Is this more secure? Or is it artificially limiting the possibilities? So there's this question of, have you really defined a system that is secure enough? And you can sort of look at this game and try to argue, well, it captures the property we want, but you're not really arguing about the system, you're arguing about the game. So in this series, we're going to try to answer these two questions using universal composability. Which, first of all, it gives you an explicit understanding of what it means to compose algorithms, and in which cases they remain secure. So it composes universally, which is to say in any environment. No matter what else happens around the system, it still composes and still has security. Okay, so that's what we're trying to do. And in the next seminar next week, I'm going to really introduce what universal composability actually is. But I'm just going to show you two examples where just reasoning about this using the game approach kind of breaks down. So I'll go back to the first board. Composition. So let's explore an example where these game-based definitions actually fail to compose. Two systems are secure in isolation, but when you put them together, you have no security whatsoever. Okay, so we consider the one-time pad. This is a symmetric cipher, so there's only one secret key. And you encrypt with the secret key. And the idea is the generation algorithm samples a key uniformly at random from bit strings. The encryption algorithm simply takes the message and does a bitwise XOR with the key, or if you like, addition modulo 2, same thing. And the decryption algorithm does the same thing. Take a ciphertext, XOR it with the secret key. Now, because if you add a number modulo 2 twice, then you don't change the result. This is a correct cipher. It's called the one-time pad because you can prove, I mean, it's deterministic, right? So you can prove that if you use the same key multiple times, you get absolutely no security. You can only use the key once. And this is what Claude Shannon, when he was working out information theory, first studied, and it's actually the only perfectly secure cipher. It's the only cipher that is secure, assuming absolutely no computational limits. And the idea for this is, if I take a key uniformly at random, I XOR it with any message, the resulting bits are still uniformly random. So you learn nothing by seeing the ciphertext. Okay, so it's correct. It has perfect security. The probability of any message given the key, the probability of a ciphertext given message A and the key is equal to the probability of a ciphertext given message B and the key. They are exactly equal. Okay. And then we have quantum key exchange, which is a little bit exotic. Don't worry, you don't need a degree in quantum physics to understand this idea. So the idea is, okay, we have a perfect cipher, but first we need to agree on a key. If we don't share a key, we cannot communicate using this cipher. Quantum key exchange is perfectly secure, and it allows two parties agree on a secret key. And reveal nothing to an observer. Okay, so if I use quantum key exchange to share a key, then I encrypt with the one-time pad, it should be perfectly secure, right? But it isn't. The two definitions of security do not compose with each other. Does anyone want to hazard a guess at what goes wrong here? It's down to exactly what quantum key exchange is supposed to do to be secure. The idea is Alice and Bob do some quantum entanglement business. At the end, everyone measures their state. Alice and Bob have a key that is completely independent from what any observer sees. What goes wrong here? Anyone who's maybe thought about quantum physics before? So the problem is the security definition says, if everyone measures their state immediately afterwards, then there's no information leaked. The problem is, if you send a message with the key, the observer has not yet measured their state, they can extract some information after seeing the key, after the key influences their entangled state. So because the definitions are kind of isolated, the one-time pad only thinks about the encryption, the key exchange only thinks about key exchange at the beginning, they do not compose. In fact, the property doesn't hold. Now, what you need to ask your quantum key exchange to actually have a stronger property for it to compose. And this was a thesis by a former student of my supervisor's that explored this question. So the problem with these game-based definitions is you don't know for sure whether the security actually fits together. Okay, I move on to the second board and we can discuss this strength question. The ball is here. So in our Cpa setup, we assumed that the adversary could encrypt messages, whatever message they want, but we also assumed they could never decrypt any messages. Now, this might seem like a reasonable assumption, right? if the adversary can decrypt messages, then, well, there's no security. But in a lot of practical cases, it's possible to obtain a decryption of a ciphertext you chose. So for example, if you log into a web server, then you have a private session and you can have the server decrypt some of your information that is only supposed to be between the two of you. But this isn't captured by our definition. We assumed the adversary could only ever encrypt things. So even if the server is decrypting stuff that the adversary is already supposed to know, this doesn't present a privacy issue, or shouldn't present a privacy issue for the other users, but our game doesn't capture it. So we introduce a new game, the Cca Game, to try to capture this. Chosen ciphertext attack. The idea is the adversary can, in some cases, choose a ciphertext and get the decryption of it. But obviously it can't get a decryption of whatever it wants, right? Only a few specific things. And it works as follows. So the challenger, once again, selects a key according to the generation algorithm. Oh, just gen, right? And it's going to send the key to the adversary. Now the adversary is allowed to get the decryption of as many ciphertexts as it likes. So the adversary can choose a ciphertext. The curly C is for ciphertext, not challenger. And the challenger is going to answer this by decrypting it. So the idea of this scenario is the adversary and the challenger are connected to each other, and the adversary is asking for some decryptions that it is authorized to access. So it's allowed to access these in this context. And it can do this as many times as it wants, with some caveats to do with, efficiency, right? It can't ask for exponentially many ciphertexts because it has to be efficient. Now, the adversary is going to do the same thing, choose two messages, and send them to the challenger. And the challenger is, again, going to encrypt one. So it flips a coin. And it's going to send the encryption of the message that it chose at random. Okay, so now the adversary is allowed to once again ask for decryptions of ciphertexts. I should say, I will call this encryption C hash. So the adversary is again allowed to ask for as many decryptions as it wants, as long as it doesn't ask for the one it's supposed to be figuring out, right? So the adversary can once again get as many decryptions, decrypt some stuff, do some authorized activity. But of course, it can't just ask for the decryption of the ciphertext it got, because otherwise that would trivialize the game. Repeat step 2, but C cannot equal C hash. And at the end of all this, the adversary is going to output another bit. And of course, the adversary wins if the bits are equal. So this game is capturing something a little bit stronger, and it captures, in particular, it captures what's called malleability. So imagine that the adversary gets the challenge ciphertext, C hash, and it says, well, I can't just decrypt this, the game won't let me, but maybe I can change it to a related ciphertext that isn't equal, right? If I have a homomorphic property, maybe I can double the challenge ciphertext. Then I ask for its decryption, and I know that if I halve the ciphertext, if I halve the message, then I'll undo this, right? So malleability is about relationships between ciphertexts that it can exploit. And this game does not allow, if the system is secure according to this game, it cannot possibly be malleable, because otherwise the adversary could just modify the ciphertext in a known way and win the game that way. So it's saying this is a much stronger condition, right, than in CPA. It's saying not only can you not tell ciphertexts apart, but you actually can't extract any useful information, any useful relationships between ciphertexts either. And the question is, okay, well, this is clearly stronger. If you want to think about it, you might be useful to come up with an example of how you could have an int CPA system that's not int CCA. But the question is this as strong as we need? Is this somehow too strong? Right? Maybe we're discounting systems that work totally fine, but don't satisfy this property. And these game-based definitions don't really give us any way to understand the strength. We can understand it relatively, but we can't say, is this what we need for our situation? So this weakness, the strength question, and also the lack of composability are the two issues in this framing of cryptography that we'll try to answer. And in fact, I claim this definition. Yeah, sorry.
Sorry, what does the word strong mean here?
Right. The word strong means a system is stronger if fewer things. So a definition is stronger if fewer things satisfy it. Right. So
it's not like a
CC, chosen ciphertext, right? Chosen ciphertext attack systems, secure systems, are stronger because there are things that satisfy chosen plaintext attack security, but not this. So this is asking more of the system. The system is somehow more secure against a wider range of possible attacks. Does that make sense?
Yeah, I think so. Maybe this is part of the general theory you're going to present, but I feel like I think I don't really understand the general notion of game and system and the way in which like the system plugs into these games seems like implicit but important.
Yes. This is exactly the problem I have with much of crypto literature. If you really dig into it, the parties are interactive Turing machines. The game is somehow supposed to be like a coordinated Turing machine that makes these two algorithms interact with each other according to specific rules. But this is never explicitly spelled out, right?
But it's also like too general, right? Like basically that's that's almost any possible interaction between two things, right? That's almost like saying the crypto system plugs into the game in an arbitrary way, but clearly, like in the examples you've presented, it's somehow rather specific. Well, okay, it's not really a question. I'm just trying to work my way around these definitions.
Right. So the definitions are pretty vague, right? They're all quite vague.
Okay, I apologize for this cat.
No, it's an important observation. You're totally right. The definitions are vague, and it's not clear. I mean, it's not clear what the mathematical object even is, right? It's not clear what type it has as such. Someone is drawing.
Yeah,
it's not clear what type it has. It's not clear how you construct it. It's pretty vague. And indeed, if you dive through the literature, 95% of the time you won't find an explanation. There's just the question is somehow avoided. So indeed, the universal composability is one attempt to actually make this mean something mathematically. I actually claim that in Cca is too strong. I can cook up an example that argues that this definition is somehow excluding things that it shouldn't. And it works as follows. Is my pen?
Oh,
I can't draw.
You're not able to write. Yeah, I had to turn the boards off for guests because of the decoration that we had. You should have permissions, but it may not have updated correctly. So, with apologies, you might have to just quit out and come back in.
Orally. Okay.
So if you quit and then return, you could walk into that portal over there and come back, or
all right.
Quit.
We could. I mean, you could just turn it back on for guests because the guy did leave.
Yeah, he got kicked by somebody. Yeah, okay, that's probably a good solution. Yeah, I'll keep an eye out. It's so strange that somehow this happens to Eleanor and never happens any other time. I don't know, it's just very bad luck. Okay.
Let me know. There we go.
Continue,
okay.
Yeah.
So, yeah. So the idea is we'll take a Ind Cpa system. Oops. But in fact, we'll take any Ind Cca system. So take a system that satisfies this, and then we'll change enc. We'll change the encryption PKM to be the secure encryption, but we'll concatenate a bit where the bit is just chosen uniformly at random. And we'll take the decryption to, whoops, that should be a C. And the decryption will just ignore this random bit that we tacked on at the end. I guess I'll use Python notation, right? Just drop the last bit, truncate the last bit. So suddenly, we've added a random bit that doesn't do anything. It doesn't have any information, doesn't contain anything about the message, nothing at all, but this isn't Cca secure. Right? Because what the adversary can do is take the challenge ciphertext, invert the last bit, and then it gets a decryption, it gets the message, so it can win with 100% probability. But somehow this seems a bit silly, right? It shouldn't be possible. This didn't give you any information, and yet it no longer satisfies the definition. So this is an example of all these weird definitional issues that you run into if you really chase this down. And there are some attempts at resolving this as intermediate conditions. Like there's games that have a security between the two, but no one's really settled on a standard answer here. It kind of reminds me of the whole business in the 18th, 19th centuries when mathematicians were formalizing analysis, right? And you have Fourier come in and say, hey, look, all of these kind of converge, but this convergent series doesn't do the right thing. So what are we going to do about it? And the answer was, okay, we have to have uniform convergence. We have to introduce these stronger ideas to separate out what is allowed and what isn't. And the problem with cryptography is that we don't have a roadmap for this, right? We don't really have any instructive way to figure out what the right definition is. So to summarize today, we've talked about what a cryptographic system is. Again, we didn't define it, but we did say, okay, I've got some efficiently computable algorithms that do something. They have a correctness condition. And security was interpreted as the probability that an adversary could tell apart two ciphertexts or in a meaningful way, defined by the probability that they win a game. And then an asymmetric cryptosystem, it satisfies one of these two conditions. One of them is somehow too weak, one of them is too strong, and it's not clear how to separate this. So next week we're going to zoom out a bit, look at a more general setting, and that will give us an inkling for how we can piece these theoretical ideas together. Okay. How are we for questions?
Thanks a lot, Eleanor. Yeah, what is cryptography?
Yeah.
So, like, not the definition that I'll read somewhere or other, but like, what is the deep content of cryptography? So, is it like?
Such a dating question.
I'm gonna have a jump on your head, Billy.
Yeah.
I guess I mean something like, okay, I could say I can exchange resources like computational time in order to arrange for certain laws to be true with certain probability. I mean, that's roughly how I would describe, say, a blockchain, for example, right? You can spend resources to make certain things true, even if other people don't want them to be true, adversaries with high probability or something like that. But I struggle. I mean, I guess I'm trying to identify the principle by which I process the kinds of definitions you're giving me to see whether they're right or not. And absent a principle like that, it's sort of difficult for me. So yeah, what's your answer?
Yeah. So I'd start by saying that we don't know. That is the first answer. If I think back to the question that you posed on that fine 2018, was it afternoon? I think it was afternoon, as to what is space. We're in a much better position to answer that question now than we were, say, 300 or even 200, or maybe even 100 years ago, right? We kind of can answer that question in mathematics. Cryptography is a much younger discipline, and I would argue that we haven't really figured out what it even is yet. I mean, cryptography only started to exist. First of all, we had to have Turing come along and study models of computation. And then we had to have Shannon study ciphers. And even then, it wasn't until the 70s when Diffie-Hellman, Rivest-Shamir, Adelman sort of invented non-trivial crypto stuff that we really started to have a field that was sensibly cryptography. So we don't really know yet. My perspective on this is cryptography is about, first of all, it's about what I call a system. And a system is some object that I can give it some inputs, and maybe other parties can give it some inputs, and it gives me outputs. So a blockchain system, for example, I give it my transactions, other parties give it their transactions. I can query it to find out the state, and it answers my queries. And then, once we've got the idea of a system, we want to figure out what properties, what conditions hold on the outputs. So for a blockchain, we have conditions like, for example, no double spending. It shouldn't be possible for someone to spend a token twice. So to my mind, we have this nebulous idea of a system, which I will pin down more in the coming seminars and also in my PhD. And then we want to figure out how to require that it behaves a certain way. And as you say, what separates cryptography from, say, just algorithms as a field of study is that really we have to make sure these conditions hold, even if people are trying to sabotage us. That's what, I guess, separates cryptography from other related disciplines.
Yeah, I think that's part of the reason I find cryptography very interesting, and why I find cryptocurrency so interesting, because it's clearly so profound, right? The idea that you can take laws or propositions that are just not true and like arrange for a little corner of the physical universe, like a set of communication channels, say, where they are true, or at least, approximately true, or with high probability true. That general idea is so interesting.
Yeah, I think it's one way to understand where cryptography, or especially in the distributed systems like blockchain-y context, comes from is distributed algorithms, Byzantine fault tolerance, right? This started by imagining, okay, we don't imagine that the servers are conspiring to get us. but we imagine that they just happen to fail in such a way that the worst possible thing happens. And then we started to say, okay, but what if they are trying to conspire against us? Yeah, I totally agree. It's just, as you say, we take things that are just not true, and by relying on computational assumptions, typically, we somehow arrange that they happen to hold, at least with very high probability.
Wait, I'm not following this analogy about what are the things that are just not true that become true in some way?
So, for example, it is not true that if I send you a message that is not, so I send you a message, and someone else also sees the message, and then I do it again. As soon as I do it again, it is just not true that the messages have no information, right? I cannot possibly, if I'm trying to communicate with you, as soon as I've sent two messages encrypted with the same algorithm, then they must, according to information theory, they must contain information about the plain text. They have to.
Right.
But by relying on certain assumptions, we can arrange it so that, okay, yes, they contain information, but the probability you can make use of that information is so tiny that we can ignore it.
Right. So there's something related to the idea of, like, the idea of information is in some sense kind of preliminary, right? Because it's, I mean, information's hard to understand as a concept because it's subjective in some deep way, right? What is information to you is not information to me. And I always feel like cryptography is pushing on the part of that definition that you sort of don't want to look at, which is exactly that point about, well, it's information to me and not information to you, right? Yes, yeah, very interesting.
Yeah,
Okay.
I mean, a lot of these theories are trying to understand what that even means, what information being useful somehow means. And that's where this idea of computational distinguishing games comes from. It's like the information is useful somehow if it can help you win these games. That's the spirit behind it.
Yeah. Cool. Thanks, Eleanor.
No worries. Thanks for coming along.
Yeah.
I will be back here this time next week.